Welcome to the EEE 350 Midterm 2 Practice Exam Review session. My name is Walker Krabakian. So first, I'll begin with a quick overview of what we're going to be doing today. I'll start by giving you some general tips on how to study. Most of them will be pretty similar to what I said for the first midterm, but I'll give you some more tailored advice for this exam because it tends to be a little trickier. Then I'll review the questions on the practice exam, which you all had access to. And finally, I'll allow you all to unmute yourselves, and then you can ask me any questions you have about the exam or the course in general. For now, you can't unmute yourselves, so if you have any questions, post them in chat, and I'll try to answer them as soon as possible. All right, so first, some tips on how to study. So my #1 piece of advice is review the practice exam for midterm 2, right? If you look at the first exam, it was very similar to the first midterm. Yes, I will be posting the unannotated and annotated versions of these slides along with the recording after the review session is over. All right, so some general tips on how to study. First, review the practice exam. If you look at the first exam, it was very similar to the first practice exam. You can probably expect something similar for this exam. Also review the results of your first midterm. If you made any mistakes, make sure you figure out what you did wrong so you don't repeat them on this exam. The material in this course is very cumulative, so we're going to be dealing with the same sort of topics, although they'll be a little more technical in this exam. My second piece of advice is prepare your formula sheet. Like I said, this exam is a lot more technical than the first exam, so there's a lot of different distributions and functions to keep track of, and it can really help if you have all the integrals listed on your formula sheet. So I'll give you some examples of things you should put on your formula sheet. And let me check. In the information, in the announcement for midterm 2, it mentions you're allowed just one sheet of formulas. So yeah, so just like the first exam, you have one sheet of formulas allowed, and calculators are allowed, so make sure you have a calculator ready. And my third piece of advice is to review the lecture slides. There are a lot of examples in there to make sure any missing gaps in your knowledge are fulfilled, right? So make sure you pay attention to the lecture slides because yeah, those examples can really help your understanding. But like I said, the best piece of advice is review the practice exam because a lot of the questions are very, very similar. Maybe the numbers will be changed a little, or the wording might be changed a little, but the way you solve it is very similar. So review the practice exam. All right. So on to some topics for midterm 2. If you're looking for the textbook, these are the sections to pay attention to. Most of the material is from chapter 4 and chapter 6 if you're in the second edition, or I believe, let me check, chapters 5, 7, and 9 in the third edition. I've separated them into a few different categories. So for the first category, sections 4.1 through 4.5, it's really just getting you accustomed with the idea of mixed random variable distributions, right? And there's a lot of analogs to what we saw in the first midterm for single random variable distributions, right? So CDF, PMF, PDF, all those terms should look familiar to you. And in these sections, we define the joint CDF, the joint PMF, and the joint PDF to describe a random distribution of 2 or more variables, right? In these sections, it discusses how to get the marginal PMF and the marginal PDF given a joint PMF or joint PDF. What that means is going from a distribution of 2 random variables back to a distribution of 1 random variable, right? So this is for a PMF, and for a PDF, it would be this, right? So make sure you know how to do this because this will definitely be on the exam. Then in the second category, we have sections 4.6 through 4.9. This is dealing with how to find statistics on derived expressions of joint random variable distributions, right? So we're talking about expected values, we're talking about variance, covariance, correlation, conditional probabilities, conditional expected values, right? It's really just a lot of what we talked about for the first midterm, but applied to mixed random variable distributions. So yeah, there's lots of useful formulas in these sections. Then there's some other properties of joint random variables, maybe some joint random variable distributions. The bivariate Gaussian random variable is probably a good one to put on your formula sheet because it's really long and complicated. The rest of these, you should still understand the definition of independence from the first midterm. And there's a more precise definition when it comes to relating the expected values of joint random variables. And finally, in chapter 6, we talk about the moment generating function. So this is another acronym to remember, MGF, right? The moment generating function, which is represented by phi, and how that relates to the moments of a random variable. So we'll talk about that in one of the questions. So yeah, these are the topics to study. And these are the sections from the second edition. And I also have the sections for the third edition. So it's probably a good idea to scroll through those sections and keep track of any formulas because a lot of them will show up on the exam. All right. And I think with that, we're ready to begin reviewing the practice exam. So, all right. Problem 1 of the second practice exam. Consider the joint PDF of two random variables x and y given by little f x comma y equals c, where 0 less than or equal to x less than or equal to y less than or equal to 4. Find the constant c. So in the first midterm, we had the concept of a singular random variable PDF, right? Which sort of represented the probability of a continuous random variable falling within a given area, right? The density, if you will, the probability of it falling within that area divided by the area, right? As the area gets really small. And we extend that definition to multiple random variables, right? So this gives you the probability density of it being in close to the coordinates x and y, right? And here I have some some properties of the joint PDF. And we can notice that they're pretty similar to the properties for the singular random variable PDF, right? For the singular random variable PDF, we had that it had to be greater than or equal to 0, right? This just comes from the axiom of probability that says that any probability is non-negative. And the second property, which is what we're going to need for this problem, is that the integral over all possible values of the random variable of the of the PDF has to be 1, right? And this just comes from the axiom of probability that says that the probability of the sample space is 1, right? So we're going to be using this property for this problem, right? The integral of all possible values of our joint random variable has to be 1, right? So if we apply that in this question, well, the PDF is pretty simple. It's just a constant, right? But the hard part is finding the bounds for this double integral, right? So I think I'm going to integrate with y on the outside, right? And if we look at y can be anywhere from 4 to x, but even more broad than that, we can say it can be anywhere from 4 to 0, right? So if we're putting y on the outside, our bounds would go from 0 to 4, right? And then for our inner integral, in terms of x, the bounds are from 0 to y, right? So this is going to depend on the outer variable, right? And then our PDF is just C, right? So this would be C, dx dy. And we're going to set this equal to 1. All right, I kind of drew this a little big, so I might have to go down a little bit. So if we're going to evaluate this integral, the inner integral is just going to be cx, right? So 0 to 4 of cx from x equals 0 to x equals y. Right, and this is just going to be cy, so yeah, this is kind of won't rewrite it, but this is just going to be the integral from 0 to 4 of cy dy, which is going to be cy squared over 2 from 0 to 4. And that's going to be 8c, right? So this double integral gives us that 8c is equal to 1. If we solve for c, we get that c is 0.125. So the key part of this problem is setting up the bounds for our double integral. You should definitely have these properties listed on your formula sheet because they're very important. And just pay attention to how the random variable distribution is defined, right? When you're trying to figure out these bounds. All right, so that's the first problem. And on to the second problem. So, like I said, if you have any questions, post them in chat, and I'll try to keep track of them. All right, problem 2. Suppose random variables x and y are related as y equals 6x plus 3. Suppose the random variable x has mean 1 and variance 1. What is the expected value of x plus y? So I have here some good equations for the expected values of derived random variables, right? If we know y is 6x plus 3, then x plus y is just going to be 7x plus 3, right? So our sum is just going to be 7x plus 3. And if we want to use this formula, because we're trying to find the expected value, then a would be 7. So e of 7x plus 3. This is going to be 7 e of x plus 3. And if the expected value is 1, that's a bad 3. Right. If the mean is 1, right, the mean is just another way of saying the expected value, right? So e of x. Then we just plug in e of x is 1, and we get 7 plus 3. And that's going to be 10. So finding the expected value is pretty simple, but one thing I'd like to point out is if they ask you for the variance of a derived random variable like this, you don't just add the variances, right? That can be true if the random variables you're adding are independent, then you would add the variances. But if you're just multiplying a random variable x by some constant a, right? We don't multiply the variance by a, we multiply it by a squared, right? And that should make sense based on the definition of the variance, right? The variance is var of x is the expected value of x minus the mean of x squared. we're asked for the expected value of x plus y. So if y is 6x plus 3, then x plus y is 7x plus 3. So when we go for the final answer, we are going to be using 7x plus 3. So yeah, make sure you pay attention to what it's asking for, because yeah, it's not asking for the expected value of y, it's asking for the expected value of x plus y. But anyways, as I was saying, the variance is the expected value of x minus mu squared, right? So if we multiply x by a, then this becomes e of ax minus a mu squared. And we can factor a squared out of this, and this is just going to be a squared times the variance, right? So like I said, the variance of ax is a squared times the variance of x, right? So yeah, that's kind of tricky. I have here some theorems for, in general, if you wanted to find the expected value of a sum of random variables or the variance of a sum of random variables. And you can derive these theorems from the lower theorems, right? But yeah, for the exam, definitely know these two properties, right? They probably will show up in some form. But yeah. All right, so that's all for the second problem. And on to the third problem. So question 3. Suppose we have a coin that has a heads probability of 0.4. Suppose we flip that coin until we get our first heads. The random variable x is the total number of flips we had to make. Find e of x. So like I said, this course is very cumulative. We definitely talked about these sorts of problems in midterm 1. So I'm going to write that. Midterm 1. So definitely review your first midterm, because the same sorts of problems will be asked. But for the most part, you can expect new material. But anyways, for this problem, we're talking about flipping the coin until we get our first heads, right? And whenever you're talking about doing a repeated experiment with the same chance of a success until you get your first success, you're dealing with a geometric random variable, right? And I have the PMF of that here. Now, we don't just want to find the probability, we also want to find the expected value, right? And for discrete random variables, to find the expected value, we have to add up each possible value of the variable multiplied by the PMF at that value, right? So this is going to be the sum of, so this is going to be the sum of x times the PMF, which is p times 1 minus p to the x minus 1. Right. The way I like to evaluate this, I mean, there are definitely a lot of ways, there are a lot of good ways to evaluate this, is I like to list the first few terms. So the first term is going to be 1 times 0.4, right? Because we're flipping until we get our first heads. The second term would be 2 times 0.4 times 0.6. The third term would be 3 times 0.4 times 0.6 times 0.6. The fourth term is 0.4 times 0.6 times 0.6 times 0.6, right? And what we can notice is that for each of these, what we can do is we can write this as a sum of a bunch of different sums, right? So the first thing we're going to write this is as 1 times 0.4 or plus 1 times 0.4 times 0.6 plus 1 times 0.4 times 0.6 So what I'm doing is I'm going to take one of each of these, right? And if we subtract this from this, now we're going to have 1 times 0.4 times 0.6 plus 2 times 0.4 times 0.6 squared plus 3 times 0.4 times 0.6 cubed, right? So effectively, by taking this lower sum out of this upper sum, we've shifted all of the coefficients one to the right. So I can add on to this the same sort of thing. So now I'm going to take one more out of each term. And now this term will be completely covered. This term will be completely covered. This term will now we're going to have 1 times 0.4 times 0.6 squared. And here we're going to have 2 times 0.4 times 0.6 cubed. And so this lower sum, when we subtract that out, we're going to shift all of the coefficients one more to the right. And if we just keep doing this, eventually we're going to cover every single value of in this upper sum, right? So to calculate this upper sum, we just need to calculate the sum of each of these infinite series. And what we can notice is each of these infinite series is itself an infinite geometric series. And that has a pretty simple formula, which you should all know. So sorry if that was a bit complicated, but effectively what I'm saying is this is the same thing as a double sum. So this is going to be from I equals 0 to infinity. Sorry, j equals 1 to infinity of sorry. Yeah. Okay. Sorry. Okay. Okay, yeah, so the coefficient, effectively what I'm trying to do is I'm trying to get x, this x factor out of the coefficient, right? Because if we were doing this sum, we would go from x equals 1 to infinity, and there's no really easy way to do that. By taking each of these individual infinite sums, now the coefficient becomes 1, and then there's a formula we can use, right? So this would be 1 times p times 1 minus p to the I times 1 minus p to the j. Right? Where the this factor, 1 minus p to the I, determines which of these sums we're talking about, right? So when I is 0, we're talking about this upper row because the first term doesn't have a factor of 0.6. When I is 1, we're talking about the second row because the first term does have a factor of 0.6. I guess j should also go from 0 to infinity. So on, right? So we're taking an infinite sum of infinitely many geometric series, right? And sorry, if this is all too complicated, don't worry. All you really need to know is the final answer. So we can evaluate this inner sum because this inner sum is an infinite geometric series, right? The common ratio is 1 minus p. Why did j's lower limit? J goes from 0 to j goes from 0 to infinity because the first term the factor of 0.6 in the first term is uniquely determined by I, right? So j should always be 0 in each of these first terms, right? Sorry if that's a bit complicated, but there's no x in that stuff. Yes, because now effectively what I'm doing is if you add up all of the coefficients, right? So I guess I should put a line to separate these, right? If you add up all the coefficients here, they add up to the top, right? 1 is just 1. If you add up all the coefficients here, 1 plus 1 is 2, right? If you add up all the coefficients here, 1 plus 1 plus 1 is 3. All the coefficients here, there would be another sum down below, right? 1 plus 1 all the way up is 4, right? The point of all this messy math is to get rid of this x factor, so now we can write it as a bunch of infinite geometric series, right? So if we evaluate this inner infinite geometric series with the property that the sum from I equals 0 to infinity of a r to the I is a over 1 minus r, right? This is the sum of an infinite geometric series. You should definitely know this. Sorry, I didn't put it in this slide. I really should have. But I'm going to use this formula to evaluate this inner sum, right? And that's going to be, so this is the sum from I equals 0 to infinity of the first term is going to be, so a up here is just going to be 1 minus p times 1 minus p to the I. So this is a. And then r is just going to be 1 minus p, right? So this, once we evaluate the inner sum using this infinite geometric series formula, right? This is going to be p times 1 minus p to the I divided by 1 minus the common ratio, which is 1 minus p, right? And if we evaluate this, this is just the sum from 0 to infinity of 1 minus p to the I. And when we evaluate this outer infinite geometric series, right? So now the first term is just going to be 1 because 1 minus p to the I is 1 when I is 0. And the common ratio is still 1 minus p. So, so the final series is going to be 1 divided by 1 minus p. And this is just going to be 1 divided by p. So it was a lot of math. Sorry if that was confusing, but now that we have this, you can just write this down. This is the expected value of a geometric random variable, right? So I definitely advise putting the expected value of each common random variable distribution on your formula sheet so you don't have to do all of this math during the exam, right? So if p is 0.4, then our answer is just 1 divided by p. So 1 divided by 0.4, that's going to be, I believe, 2.5. Yeah, so sorry if all that math was really confusing, but the important part here is the final answer, right? It's going to be 1 over p. So if anything, just put that on your formula sheet because chances are you won't be asked a more complicated expected value if you encounter a discrete series on the midterm. All right, so that's all for question 3. Sorry if that was a handful. It's tricky to solve if you don't have the formula in front of you. But once you have it, it's pretty easy, right? It's just 1 over p. All right. On to problem 4. So Problem 4. Consider a joint PDF for random variables x and y given by little f x comma y equals cxy for 0 less than or equal to x less than or equal to 1 and 0 less than or equal to y less than or equal to 1. And little f is 0 outside of that range. Find the constant c. So this is pretty similar to the first problem, right? We just evaluate the double integral. And the bounds are really easy this time. It's just going to go from 0 to 1 for both random variables. So the order of integration doesn't really matter. Of cxy, dx, dy. So if we do the inner integral, it's going to be integral from 0 to 1 of cx squared y over 2 from 0 to 1 y. So if you evaluate that, you're going to get the integral from 0 to 1 of cy over 2, or sorry, dy. And then this is going to be cy squared over 4 from 0 to 1. And that's just going to be c over 4. And if we set all of this equal to 1 and solve for c, we get c equals 4. So that's our answer. So yeah, definitely have this integral on your formula sheet because I think a bunch of the problems are based on this property. So yeah, so that's a good one to know. All right. So that's all for problem 4. On to problem 5. So problem 5. Consider a pair of random variables x and y, each of which take on values on the set a equals 1, 2, up to 7. The joint distribution of x and y is a constant for all x comma y pairs coming from the set A above. Let the random variable z be given as the maximum of x and y. Find the probability that z is equal to 2. Okay. So first we need to find what the PDF or what the PMF should be, right? This isn't that complicated, right? If we have 2 random variables, x and y, and each of them is over the set 1 up to 7, then we have 7 choices for x and 7 choices for y, for a total of 49 possible choices. And if each of them are equally likely, then the probability of any individual combination is just going to be 1 over 49, right? There were a bunch of questions on the first exam that where we were sort of doing this, right? Like the one that was about counting license plate numbers, right? Where you have a license plate built from numbers and letters of the alphabet, and you would have to do this sort of math. Well, now we're using it to find the PMF, right? So once we have the PMF, we're just going to add up the PMF for every combination where z is 2, right? So if we want to find the probability that the maximum of x and y is 2. Luckily, 2 is pretty small, so we can just count them. The combinations are 2 and 1, right? 1 and 2, and 2 and 2. So 3 combinations. So our answer is just going to be 3 times the PMF, the PMF, the probability of any individual combination. So that's going to be 3 over 49. And let me get out my calculator, because you have to enter this as a decimal. 3 divided by 49 is 0.061. So yeah, this is definitely one of the simpler problems. in general, whenever you're dealing with a uniform random variable, right, one where every possible combination has the same likelihood, right, you just find the total number of combinations and divide 1 by that number, right? So, yeah. All right, on to problem 6. Problem 6. Consider 2 random variables. What happens if it was a bigger number that might be hard to calculate by only counting? Okay, thanks for that question. Yeah, that is a good question. And this is the Fencepost problem, which I mentioned in the first midterm review. If it were, for example, let's say our set was b equals 5, 6, 18, right? Something like this. Is this what your question is talking about? I think it is, but yes, okay. So yeah, if this were our possibility, we would do, if this were the problem, we would do the same sort of thing, right? Where we count up the number of possibilities for x and y, but when counting them, you have to be wary of the Fencepost problem I talked about before, right? This isn't just going to be 18 minus 5, it's 18 minus 5 plus 1, right? Because we have to add 1, because if we just take the difference, that's only going to include one of the endpoints. We want to include both of them, right? So the total number of possibilities is just the difference plus 1. And we would write that for each of x and y, multiply them. So now we would have 196 combinations, right? Plus both number, max number. Yeah, that's right. So yeah, definitely reviewed the Fencepost problem, which I talked about in the first review. Yeah, no problem. Yeah, if you have any other questions, just post them in chat. That's what the review session is for. So subtract the smaller number from the bigger number and then add 1, right? You have to add 1 when it's the discrete case, right? If it's the continuous case, then you just take the difference, right? I wish I had a picture of a Fencepost in front of me, but yeah. All right. So problem 6. Consider 2 random variables x and y which have a joint distribution given by little f x comma y equals c x squared y, where 0 less than or equal to y less than or equal to x less than or equal to 1, where c is a constant. Suppose w equals 3x plus y. Suppose we express the CDF of w in the usual double integral form. I'm not going to read all of this, but where w equals 0.6 is a given value at which we would like to evaluate the CDF of w, right? So in this CDF, we're dealing with possibilities where w, 0.6, is equal to 3 little x plus little y, right? Whenever you're talking about a specific value of a random variable, you use the lowercase, right? So w equals 0.6 would mean 0.6 is equal to 3 little x plus little y. The inner integral limits g and h are potentially functions of y. The outer integral limits a and b are constants. What is the constant b? All right. So given that the sum 3x plus y is 0.6, we want to find the bounds on y, right? However, we have the extra condition that y is less than or equal to x, right? So first, what's the minimum possible value of y? Zero, right? That's given to us in the definition of the random variable, right? Y has to be greater than or equal to 0, right? So the lower bound a, that's easy, right? A is 0. Now for the upper bound, the naive answer would be 0.6, right? Because if x has to be non-negative, then the minimum possible value x could be is 0, and therefore the maximum possible value of y would be 0.6, but that's not correct because we have this extra condition, y is less than or equal to x, right? So whatever our maximum value of y should be, the value of x corresponding to that has to be greater than or equal to it, right? So let's say our maximum value of y is y prime, right? If this is a true maximum, then we must have x prime is equal to y prime, right? Because that's going to be the minimum value of x that satisfies this condition, right? So therefore, 3x prime plus y prime is equal to 0.6. And because x prime is equal to y prime, we can write this as 4y prime, right? So 4y prime equals 0.6. That's a bad error. Y prime is equal to 0.15. So that's the maximum possible value of y, and that means b has to be the maximum possible value of y, which is 0.15. Sorry. Yeah, so these bounding problems can be a bit tricky, but I mean, the key thing is like box anywhere where they talk about the range that these variables can fall into, right? So whenever you have 0 less than or equal to y or something like that, right? That's always going to be important when determining the bounds for these integrals. I also have this general integral here for the PDF of a sum of random variables. This came up on one of your homework problems. Unless you know that x and y are independent, you have to use the joint random variable. And I think there's something important to note here, which is whenever you take an integral, you always eliminate one of the random variables, right? So for example, if we take the integral of a one variable PDF, right, dx, this is just going to give us some probability, right? So there's no random variables, right? If we take the integral, a single integral of a joint PDF, this is going to give us something that depends only on y, right? So that's worth keeping in mind, right? The integral, sorry, let me write this out in text. The integral of a PDF always reduces the number of variables by 1, right? So to go from a joint random variable distribution with x and y to a single random variable distribution with just w, right? We have to take a single integral, right? Now, this is only for PDFs, right? The CDF isn't it technically isn't dependent on a variable, or it's dependent on a variable, but it's not dependent on a distribution of a variable, if that makes sense. That's a horrible way of phrasing it, but I think you get the idea. The idea is to go from the 0 variable case is a probability, right? And the CDF is a probability, right? It's the probability that capital W is less than or equal to this lowercase w, right? So we can always say the integral of a PDF reduces the number of variables by 1. All right, sorry if that was a bit confusing, but yeah, I think it's worth keeping in mind. All right, on to problem 7. Consider a discrete uniform random variable n over the set -9 up to +9. Let m equal the absolute value of n. Find the PMF of m evaluated at k equals 1. All right. So once again, this is something we talked about in midterm 1, because this is really just a derived random variable of a single random variable. So midterm 1. Okay, right. To find this, what we can do is we can use the definitions of a discrete uniform random variable to find the PMF of n, and then use some properties of the PMF to find the PMF of m, right? So first of all, n is a discrete uniform random variable, right? Because it just goes 1, 2, 3, 4. It just counts all the integers from a lower bound up to an upper bound, right? So this is what someone mentioned in chat earlier. The PMF is the difference of that upper and lower bound plus 1, right? So if we wanted to find the PMF of n, this is going to be 1 divided by 9 minus -9 plus 1, which is 1/19, right? So now we want to find the PMF, the probability that PM, right? If we use the definition of the PMF, PM of k, or sorry, PM of 1, this is just going to be the probability that m is equal to 1, right? And because m is the absolute value of n, this is the probability that the absolute value of n is 1, right? So what possible values are there for n such that the absolute value of n is 1? It's just 1 and -1. Thank you. Yeah. So therefore, we can use this third property down here for any event B. The probability that x is in the set B is the sum of the PMF over every combination in that set, right? So because we only have 2 combinations, so because we only have 2 combinations, we just add up 2 of the PMF of n, right? So our answer is going to be 2 times the PMF of n. So and that's just going to be 2 times this. If we evaluate that, we get 1/19. So that's 2/19. And so let me get out my calculator. 2/19 is 0.105. So that's our answer. All right. So yeah, I probably overcomplicated this one. The important part is knowing the PMF of a discrete random variable distribution. And this is that Fencepost problem I was talking about earlier, right? You take the difference between the upper and lower bound, and then you add 1 to find the total number of combinations. All right, so on to problem 8. Man, I gotta hurry because we're not really on pace. All right, so problem 8. Suppose x1 up to xn are IID, that means I believe independent and identically distributed Bernoulli random variables, each with parameter p equals 0.3 and n equals 9. Let y equal x1 plus x2 plus up to xn. Let phi sub y of s be the moment generating function of y. Find d phi sub y of s ds evaluated at s equals 0. So first, let's look at the definition of the moment generating function phi. The moment generating function is defined as phi x is the expected value of e to the power of s times the random variable. right? And that sounds horrible, but luckily for this question, we're not asked for the MGF, we're asked for the derivative, right? Let me just type that out. Right, and whenever we have the nth derivative of the MGF, that's just going to give us the nth moment, right? And the nth moment is the expected value of x raised to the power of n, right? So because this is the first derivative, we can write n equals 1, and therefore our answer is just going to be e to the power, or sorry, the expected value of y to the power of 1. A sum of Bernoulli random variables is binomial, right? Yes, that is correct. If the Bernoulli random variables are identical, which they are in this case because we're told it's IID. All right. So we just want to find the expected value of y, right? Because the first derivative of the moment generating function is just the expected value. So e of y. All right, so now we can use the property I mentioned on an earlier slide, which is that the sum of a bunch of independent random variables is just the sum, or sorry, the expected value of a sum of independent random variables is the sum of their individual expected values, right? So all we need to do is calculate the expected value of one of these x's and then multiply it by the number of them, which is, where does it say? N is 9, right? We need to multiply by n equals 9. Yeah, this notation is confusing. Let me, I should make it clear that here I'm talking n equals 1 because this is the first derivative. That's not the same thing as, maybe I'll use capital N. It's not the same thing as n up here, which is the number of random variables, right? So the expected value of an individual Bernoulli random variable, well, that's going to be the probability of success times 1, right? So this is e of x. It's going to be the probability of success times 1 plus the probability of failure times 0, right? And that's just going to be p, which is 0.3 in this case. So therefore, the expected value of a sum of I equals 1 to 9 of xi, this is just going to be 9 times p, right? You just add up the expected value of each individual x, right? And that's going to give you 9 times p, which is 2.7. And so therefore, that's our answer. All right. So yeah, this phi notation, d phi y ds, that looks horrible, but luckily, the derivative of the moment generating function has a nice form, right? It's related to expected value. So definitely have this on your formula sheet because you will need this, and you probably also should have this, right? Yeah. All right, so that's all for problem 8. And on to problem 9. Problem 9. Suppose we have two random variables x and y with joint distribution little f sub x comma y is equal to ax of negative ax plus y, where x is greater than or equal to 0 and y is greater than or equal to 0, and little f is equal to 0 otherwise. Find the probability of y is less than or equal to x if a equals 4. So it's good to point out that this exp just means exponential, right? So I'm going to write this as a equals ae to the power of negative ax plus y. That's kind of messy, so. There we go. All right. F is a times e to the negative ax plus y, right? We want to find the probability that y is less than or equal to x, right? If a is equal to 4. So to find any probability given a joint PDF, you just find the double integral of the PDF over the set, right? So if our set is y is less than or equal to x, then I think on the outer integral, I'll integrate in terms of x. So what's the upper bound on x? It's infinity, right? Because all we're given is x is greater than or equal to 0 and y is greater than or equal to 0. So therefore the lower bound is 0, right? Now what's the upper bound on y? The upper bound on y in this problem. It's x, right? You got to be careful, right? Because the problem is asking for the probability that y is less than or equal to x, in our set A, y is less than x, right? So the upper bound of y is x. And the lower bound is also going to be 0. And then we're taking the double integral of our PDF, which is a e to the negative ax plus y. So if we take the inner integral of this, we could do a u substitution of e to the power of negative ax plus y. I'll just skip that math. You should get 0 to infinity of negative e to the negative ax plus y, right? At 0 and x. And this is y is equal to 0. So if we simplify that, we're going to get 0 to infinity of, when y is 0, this is just going to be e to the negative ax. And then minus, when y is x, this is e to the negative x times a plus 1 dx. And let me make sure I'm doing this right, because this looks, oh, okay, sorry, this should be, I messed up the inner integral. This should be negative a, right? Because when we integrate in terms of y, the coefficient of y here is -1. So we would just divide this by the coefficient. So, so we wouldn't get rid of the a factor yet. So this should be multiplied by a, and this should also be multiplied. Okay. And now if we take the antiderivative of that, we can use the same sort of u substitution, and that's going to give us, okay, it'll give us negative e to the negative ax. There should be no a, plus a divided by a plus 1 e to the negative x, a plus 1. And this is from 0 to infinity. Well, luckily, at infinity, both of these go to 0, right? It would be pretty messy if they didn't go to 0. So, so we just have to worry about when x is 0. So this is going to be minus e to the a0 plus a over a plus 1 e to the minus 0, right? I'm just plugging in 0 down here, and then we subtract it because it's on the bottom of the integral, right? And this is going to give us 1 minus a over a plus 1. So our final answer, this probability, is going to be 1 minus a over a plus 1, which is 1 divided by a plus 1. And if we plug in a equals 4, this is going to be 1 over 5, which is 0.2. Yeah, so make sure you know how to do these double integrals, right? It's really just a matter of setting up the bounds and then making sure you don't mess up any of the integrals. Really, if you can set up the integral, you're in a good place in terms of understanding. And then it's just a matter of doing the math correctly, which can be tricky. One thing I'd like to mention, someone asked on Piazza about this question, and they said they were getting an answer of 0.8, and they didn't know why they were getting the complement of the answer. A good technique to avoid doing that, because I messed that up when I took this course on a few of the questions on the exams. I would give 1 minus the right answer. A good way to avoid doing that is to do what's called a sanity check, right? So what I mean by a sanity check is think about what you know about the behavior of this function, right? And based on that, say whether it's more likely or less likely that this event is going to happen, right? So if we look at this PDF, right, it's e to the negative ax times e to the negative y, right? So at large values of x, right, this is going to get smaller faster x increasing, and this gets smaller slower for y increasing, right? So therefore, if the PDF in terms of x is going down faster than the PDF in terms of y, that means the probability of high values of y is more likely than the probability of high values of x, right? So we should expect that y is greater than x, right? So whatever our answer should be, it should be less than 0.5. So if you ever got an answer that was greater than 0.5, you would know you did something wrong. So yeah, sorry if that's a bit confusing, but it can help to do a sanity check based on what you know the behavior of the function should be. All right, so that's all for problem 9. Just a lot of messy math. On to problem 10. Suppose random variables x and y are independent Bernoulli random variables with parameters p of x equals 1 and q is the probability of y equals 1, where p and q are both 0.5. Let z equal x plus y and let w equal max of x comma y. Find p of z equals 1, w equals 1. Okay, so all right, finally a question that's not too bad, right? If z is 1, then and z is x plus y, where x and y are either 0 or 1, then the only possibilities are x comma y is 0 comma 1 or 1 comma 0, right? That's the only possible way you can get a sum of 1. And in either of those combinations, the maximum of x and y, w, is 1, right? So we don't even need to worry about w in this context, right? So the probability of z equals 1, that's the probability of 1 success and 1 fail. So that's going to be p times 1 minus q plus q times 1 minus p. And I'll just write here, this is when xy is, this is when it would be 1, 0, and this is when it would be 0, 1, right? Yeah. So in either case, it would be 0.5 times 0.5. So our final answer should be 0.5. All right. So yeah, it's just a matter of understanding the definition of a Bernoulli random variable. Definitely put this on your formula sheet. A Bernoulli random variable can only be 0 or 1, right? So given that, this question is pretty easy, right? There are only so many combinations where the sum can be 1 and the maximum can be 1. All right, so done with problem 10. On to problem 11. Consider a discrete uniform random variable n over the set 1 up to 2. Find e of 1 over n minus 1 over e of n. So yeah, this question is kind of a joke because the set is so small. In general, yeah, I don't even know why I included this because, yeah, this is a discrete uniform random variable. So I think I must have misread this when I was preparing these slides, right? You shouldn't use these formulas because this is a discrete case, right? These are only applicable in the continuous case, right? If n is discrete and n is over the set 1 up to 2, n can either be 1 or it can be 2. And because it's uniform, the probability of either of those is equally likely. So e of n is just going to be 0.5 times 1 plus 0.5 times 2. And that's going to be 1.5. And then e of 1 over n is going to be 0.5 times 1 over 1 plus 0.5 times 1 over 2. And that is going to be, I believe, 0.75. This should be 0.75 minus 1 over 1.5, right? And if you get out your calculator, yeah, this is what I get for calling it easy because, yeah. This should be 0.0833. All right, awesome. Okay, now we're done with problem 11. Sorry about that. On to problem 12. Let x be a discrete uniform random variable over the set 1, 2, up to 2, I guess. What is the probability that x is a perfect square? So again, this could have been a harder problem, but it's kind of a joke because the set is so small, right? There's only one perfect square between 1 and 2, so this is 0.5, right? So finally, a true freebie, right? Make sure you don't mess up something like this. Because it's discrete, it can only be an integer, and there's only one integer perfect square between 1 and 2. So our answer is 0.5. Yeah, I don't know why I put these complicated theories or theorems when it's such a simple problem. All right. A perfect square is just anything that's the square of an integer, right? N squared, right? So where n is an integer, so 1, 2. Okay. This is, okay, if n is 1, 2, the perfect squares are the squares of those numbers. So 1, 4, 9, 16, etc. Right? Yeah. So yeah, if these terms, yeah, you need to know these terms. So I guess that could be tricky. Yeah. So I shouldn't call it that easy. All right. So on to problem 13. Consider the following joint PMF between random variables h and b. Let y equal h squared b over 2. Find the probability that y equals k where k equals 0. Okay, so this could have been a difficult problem if it were k equals something that's not 0, right? Because k has to be 0, that means h squared b over 2 is 0. And the only way that can happen is if h is 0 or b is 0. Right? So all we have to do is add up every possibility in this table where one of them is 0, right? So that would be this column and this row. So 0.0 plus 0.1 plus 0.1 plus 0 plus 0.1. So our answer should be 0.3. Now, if it were some other value, then we'd have to do some messy casework, and we would have to find every combination where h squared b is whatever that value should be. So yeah, so in general, whenever you have a PMF, you just add up the value of the PMF for every combination in that set. So it can be annoying if your set is complex. Problem 14. Consider a random variable with PDF given by little f sub x equals c times exponential of negative ax squared. Defined for all real x where a is 10. Find c. So again, we're using the same property we used in the first two problems, but now our integral is kind of nasty. It's going to be the integral from negative infinity to positive infinity of c e to the negative ax squared dx. It's really messy to derive, yeah. Okay, darn, I guess I should have put that on this formula sheet. I could bring up the textbook. All right. Yeah, I'll add this to the notes afterwards. All right. Yeah, thanks for pointing that out. Yeah, there's no way I would have been able to do that. All right, so in order for, so whenever you have e to the negative x squared is your PDF, you're dealing with a Gaussian random variable. And the values of mu and sigma in this formula, right? Those values are going to be determined by a, right? So in this case, mu would be 0, right? And then a would be negative 1 over 2 sigma squared. So we can write so negative 1 over 2 sigma squared is equal to negative a. So therefore 1 over 2a equals sigma squared, right? And then once we calculate that, to get the coefficient c, c is 1 over root 2 pi sigma squared. So and because we know sigma squared is 1 over 2a, this is just going to be 1 over root so this is going to be root 10 divided by root pi. And so that is square root of 10 divided by pi is 1.78. Okay, so yeah, off by a factor of 10. Okay, so yeah, definitely have the Gaussian equation on your formula sheet. Yeah, I didn't think to include it on the slides until now. So this would be the Gaussian equation on page 119 of the second edition. This one, the one for the PDF, right? It's pretty rare that you encounter this, so I'm kind of surprised it would be asked on this exam, but yeah, I mean, it is good to know. Whenever you see e to the negative x squared, you're talking about a Gaussian. That's really all I can say. All right, so on to problem 15. Problem 15. Let x be a uniformly distributed continuous random variable from 0 to 1. Let y equal negative natural log of 1 minus x. Find the probability that y is less than 2. Okay, so we want to find the probability that y is less than 2. And this is the probability that negative natural log of 1 minus x is less than 2. So if you rearrange this, that's the probability that negative 2 is less than natural log of 1 minus x. Raise e to the power of both sides, and you would get p of e to the negative 2 is less than 1 minus x. And then rearrange that, and that means the probability that x is less than 1 minus e to the negative 2. So, and x is uniformly distributed from 0 to 1. So this probability is just going to be 1 minus e to the negative 2. If we calculate this, we get out my calculator, 1 minus e to the negative 2 is 0.865. So that's our answer. So let me type that up here. And with that, we are finally done with the second practice exam. So I'm sorry if I made it look intimidating. Really, if you have the definitions in front of you and you really understand them, all of these problems are pretty straightforward. But I mean, it can be tricky. There's a lot to keep track of here. So yeah. So now I'll allow you all to unmute yourselves, and you can ask me any questions you have. So you should be able to unmute yourselves if you'd like to.
Just was going back to question 11. I don't think I really understood the gist of where the 0.5 was derived from.
Okay, yeah, that's okay. Someone else asked this in chat. The 0.5 comes from the fact that it's 1 over 2 minus 1 plus 1, right? Right, because the set goes from 1 to 2, right? You have two possibilities for n. They're each equally likely. So 1 over 2 is 0.5, right? Did that make sense? Or
yeah. So if that was a different set, I guess, and if you can just utilize a different set to get an example, is that possible?
Sure, yeah. So here's an example. So let's go from 1 up to 4, because yeah, it would be probably complicated if it were more than that. So if it's 1 to 4, then because there are 4 possibilities, the PMF, that this P sub n is going to be P sub n is 1 over 4, which is 0.25. And yeah, and so then the expected value of 1 over n, that's just going to be, it's just going to be 1 over 4 times 1 times 1 over 1 plus 1 over 4 times 1 over 2 plus 1 over 4 times 1 over 3 plus 1 over 4 times 1 over 4. And if we add all of this up, you would get, let me get out my calculator, 0.25 times. You get 0.356. So, and you would evaluate the other expected values similarly. Unfortunately, there's not really a nice expression for the expected value of 1 over n. Trying to think of, yeah, I can't think of an easy way to do it. I think you just have to add up all of these values. Okay, glad you understand now. Yeah, I'll upload a recording of this, and I'll try to edit it so it's more understandable. Some of the questions were pretty messy this time around, but yeah. Awesome. Yeah, if you have any other questions for me, you could reach out to my email, wcrewball, or you can post in Piazza, as someone said in chat. wcrewball@asu.edu. Will you be? Yes, I should be available to answer questions during the weekend. So yeah, just email me. You can post on Piazza. I check Piazza pretty regularly. So if you have any questions, concerns, don't hesitate. All right, if that's all the questions, I think I'll end the meeting here. Thank you all for coming. I really appreciate it. We had a pretty good attendance this time. So yeah, I'll try to add the definition for the Gaussian random variable to the notes, and I'll upload this recording to YouTube. And yeah, I think that's all I have to say. Yeah, thank you all for coming. I really appreciate it. I hope you ace this exam.